Okay, so just a comment. So I'm going to go over some Wiley problems. 3.4, 3.5, and 3.6. I'm going to push that back to be due 3/20/13 by 11 p.m. So the reason why I'm doing that is so it'll give you just a little bit more time to work on it before I give you the quiz, number 7 over 3.4, 3.5, and 3.6. Quiz number 7 will be this Thursday, and it's going to cover those 3 sections. So the last 3 sections in Chapter 3. So related rates, local linear approximation, and L'Hopital's rule. And then today we're going to cover 4.1, 4.1, probably 4.2, 4.3, I think, on the schedule to get done this week. And then, so we're a little behind. If we don't quite get to 4.4, that's okay. So there's a question on 3.6, number 57. So 3.6, number 57. We'll write this down real quick and then I'll switch over. The limit as x goes to 0 of x squared e to the x over sine squared is 7x. So plugging in x goes to 0, I have 0 over 0, right? So this is type 0 over 0. If I apply L'Hopital's rule, I get the limit as as x goes to 0 of 2x e to the x plus x, e to the x squared. Derivative of the top, right? Derivative of the first function, hold the second one, plus the derivative of the second one, hold the first. And then the bottom would be 2 sine of 7x times cosine of 7x times 7. Because this is a chain rule problem. So now if I plug in 0, I still have 0 over 0. Which is fine. Clean up a little bit. I get the limit as, let's go ahead and say this is 0 over 0. Apply L'Hopital's rule. The derivative of the top would be 2x e to the x plus 2 e to the x plus x squared e to the x plus 2x e to the x. Because I have 2 terms, and each term's a product rule. So the derivative of x would be 1, so I have 2 e to the x. The derivative of e to the x is e to the x, so I have 2x e to the x. Plus the derivative of e to the x, which would be e to the x, x squared, plus the derivative of x squared, which is 2x times e to the x. And on bottom, well, I'd have 14, because that's just a constant. Derivative of the first, hold the second one, plus the derivative of the second, hold the first. The derivative of sine, it's cosine, right? So I have cosine 7x times 7 times cosine of 7x, plus the derivative of cosine, which is minus sine, right? Minus sine of 7x times sine of 7x times 7. Drop the 7, but that's okay at this point, right? Does everyone see that? So cleaning this up, the limit as x goes to 0, I have, let's factor out an e to the x. What am I left with? An x squared plus 4x plus 2. Over 14, 7 cosine squared is 7x minus 7 sine 7x squared, sorry. Sine is cosine 0, cosine is minus sine. So if I plug in 0, e to the 0 is 1, so I get 2 on top, right? If I plug in 0 on bottom, sine is 0, but cosine would be 1. So I'd have 7 times 14. Right? So the 2 would cancel, and I'd have 1 over 49. Granted, I did. Seem reasonable? The limit
That's the pattern validation.
e to the x by sine of 7x squared goes to 0. Yep, 1 over 49. Any questions on that?
Will anything that would be on the test?
Maybe not this many
Pretty
levels.
to me.
You really don't have to simplify it here. It just makes it a little easier to see. Knowing e to the 0 is 1 is important because a lot of times students will plug in e to the 0 and say it's 0. So that's kind of your trick. So if I plugged in e to the 0 here, this goes away, this goes away, this goes away, and this is 2. And then if I plug in 0 down here, this goes away, this goes to 7, this goes to 14. So you can get it here. Probably apply L'Hopital's rule twice would be expected, yeah, about that.
Just to be clear, I mean, I think I see what you've done, but like for example, going from the really long one
This one?
to the second to the last one
Mm-hmm.
in the denominator,
Mm-hmm.
you know, the denominator ends up being 7 cosine squared of 7x. So the cosine squared of 7x is just like, you could treat that algebraically like it's just its own
Term?
term.
Yes, it is its own term.
So you don't do anything with the 7x at the end of that.
Well, if this was like pi over 2, you would have to say 7 pi over 2. The fact is 0, cosine of 7 times 0 is the same thing as cosine of 0. The important thing about the 7 is that when you differentiate it, you take the door to the inside. So you get 49 on bottom instead of...
Sure. Well, I guess what I'm saying is that like when I was going through this, when you were writing
Yeah.
that down, I was going for, like, I got 7 cosine squared of 49x, but obviously that's not correct.
Yeah.
Because just the cosine of 7x is essentially just an x in this case. And it
Yes.
becomes x squared, basically, right?
The x is not squared.
Well,
it's
no, what I mean
cosine of something times cosine of a times cosine of a is cosine squared of a,
Got it.
which is cosine of a quantity squared, not the a squared.
Right.
You plug in cosine of a and then you square that. But luckily, cosine of 0 is 1, and 1 squared is 1, and sine of 0 is 0.
Sure.
So that term goes away. Yeah, so you have to really understand what's going on with, basic functions. And honestly, you don't have to simplify it this much. You can get your answer from this problem here. When I plug in 0, I get 2 on top, and on bottom I get 14 times 7. Any other questions on Wiley? Just a comment on 3.4. A couple students had emailed me the softball problem. In the, I don't remember which one it was. The softball diamond. When you are 20 feet from second base, you're really 40 feet from first base, right? And a lot of students were missing that when they get this was home, first. My player's running from first to second. This is my triangle. So this would be 60 feet. This is h. This is changing, and x is changing. So they get the relationship 60 squared plus x squared is h squared. Then they differentiate. But they plug in x to be 20, but really x could be 40. Right? Because when your player is 20 feet from second base, they're 40 feet from first base. So that was a very common mistake on that problem. So if you email me that, I try to say that. Sometimes in an email it's hard to get that point across. So
It seems you also like put your answer in rational form.
you have to, simplify answer in fraction form. So you want to enter the exact answer. So if there's a pi in there, you leave it as pi. If there's a square root of 12 in there, you leave it as square root of 12. Any other questions on Wiley? So again, I'm going to push these three back to be due Wednesday at 11 p.m. Give you a little bit extra time, and your quiz will be over these three sections. Very similar to what you've seen on Wiley. Okay, so today we are going to cover 4.1. 4.1, 4.2, 4.3, they all are about analyzing functions. So, analyzing the graph of functions. We're going to ask the questions today. When is the function increasing? When's the function decreasing? And when's the function concave up and concave down? And that's known as concavity. Your book kind of goes about this slowly in introducing it, and I will kind of throw out these terms critical point and inflection point without actually getting to the point where we define them, but eventually we're going to define them from the book. So the goal in this section is to develop mathematical tools that can be used to determine the exact shape of a graph and the precise location of its key features. So we're going to ask, where's the critical points? Where's the inflection points? But we haven't quite got to what a critical point is or what a inflection point is. So just if we think of a graph real quick. If I graph a function, some polynomial, the x-axis, the y-axis, some function of x. This interval, my function is increasing on, right? You can see that the function is getting larger. If x values as x goes in this interval, my function is increasing. So my function is increasing. In this interval, my function is decreasing. And then in this interval, my function is constant. So do you see how if my slope is positive, my function is increasing? If my slope is negative, my function is decreasing. So I can find out information of my original function by looking at the slope. If the slope is positive, the original function has to be increasing in that interval. If the slope is negative, my function is then decreasing on that interval. So this is talking about a continuous function. So we'll take it to be known that any function we're dealing with is continuous. A lot of times we deal with polynomials. Polynomials are continuous everywhere. But as long as I can't jump, then the interval is going to be from minus infinity to infinity. So differentiating it, I don't have a problem. Because the derivative on the right is going to equal the derivative on the left type thing. When our function's not continuous, we've got to do a little bit more work on the consideration of the discontinuities. Like if I did a rational expression, 1 over x minus a, I'd have a problem at a. So I couldn't talk about the derivative at a because the function's not even differentiable at a, because the value of the function doesn't even exist at a. We'll get to it. That's about 4.4. But right now we're just assuming the function's continuous. So just to kind of shorten this up a little bit, if the first derivative is greater than 0, on some AB, some interval AB, then the function is increasing. On the closed interval AB. If f prime of x is less than 0 on AB, then f of x is decreasing on AB. And if the function, the derivative equals 0, the first derivative equals 0 on an interval AB, then f of x is constant on the AB. Eventually we'll define this as a critical point, but I'll wait until your book pulls that up. So let's look at an example.
Is it the zeros or fx?
Yes. So let's say we have the function f of x equals x squared minus 4x plus 3. And I want to know about this graph. You guys can graph quadratics, right? You guys have you've seen the tools to graph quadratic. You got to find the vertex, find out if it opens up, if it opens down, things like that. You can see that this is a quadratic that opens up. The vertex you could find by completing the square to see the shift in x and the shift in y, right? Everyone loves completing a square. Easiest thing to do, right? 2 seconds. No, it's not, right? It takes some time to complete the square. So actually here, the calculus approach to this is a lot faster than the algebra approach. The calculus approach would just say, okay, find the derivative, set that equal to 0, and find if the slope is positive or negative on each side of that. So if I was to differentiate this function, what would I have? So if I set that equal to 0, if I come over here and I find x would equal 2, right? This is the 0. So now if I look on the left side, if I go ahead and factor this like this, if I plug in a number less than 2 to the derivative, let's say I plug in 0, then I would have a negative number times a positive number, right? Negative times a positive is negative. And if I plug a number greater than 2, I would have positive here. So what this is telling me is my function is decreasing until it hit x equals 2, then it's increasing. This is known as the vertex, right, of a quadratic. The vertex is at x equals 2. Once I have the vertex, I can find the x-intercepts and I can find the y-intercept to get more information from the graph. But at this point, we don't need all the information. We just need the basic shape. The basic shape is a quadratic, right? And at x equals 2 is where is my turnaround point. My function is decreasing until x equals 2, then it's increasing. So if this had to do with some kind of maximum or minimum problem, that let's say, if I wanted to minimize price. So if I'm on this side of 2, my price is decreasing. Then some point at x equals 2, that's the minimum price I could ever get. And then on the other side of 2, my prices then be increasing. So if I want to, eventually we'll talk about maximizing and minimizing functions, and that's what it's kind of leading to. But if I was to graph this, my vertex would be at x equals 2. If I plug in 2 to my original function, get 2 squared minus 4 times 2 plus 3, I get minus 1. So my vertex is at the point 2 comma minus 1. That's the minimum value. If I was to graph this, my y-intercept would be 3 at x equals 2. My value of the function would be 1. So I'd have this quadratic. Right, I could use not Pythagorean's theorem, but negative b plus or minus square root of b squared. Quadratic formula. Thank you.
It's Monday.
I know. The quadratic formula to find these points, right? I could use quadratic formula to set when does the function equal 0. But it turns out, if I was to graph this equation, if I was to graph this equation, this 2x minus 4, that tells me this is a linear equation. It has a slope of 2, and it goes through the y-intercept at minus 4. So this is 3. So we'll pull this down a little bit. 1, 2, 3. It would turn out to be like this. Right? This would be the derivative function, and this would be the function. So you can see that the slope here is negative. So my derivative has to be below the x-axis here. This is a negative slope. This has a slope of 0, so I have to go through the x-axis on my derivative function. And then from there on out, I have a positive slope. Eventually, we'll talk more about graphing the derivatives on top of the functions. And you can do that by differentiating and graphing that. But at this point, we're focusing on intervals of increasing and decreasing. So it turns out f of x is decreasing on minus infinity to 2 and increasing on 2 to infinity. Make sense?
Is that what the question would be for
Yeah.
where it's increasing?
Yeah, so I'm going a little bit more detail with the graph and the value of the derivative on top of the graph. But yeah, here we just ask when's the function increasing and decreasing. Let's look at a next example. It may be algebraically a little bit more.
Before you go,
Okay.
I think I understand the general concept. I'm a little unsure on where in the part up there where you determined that x equals 2. Right below that you have 2.
This is just it factored,
Oh,
right? If I factor out a 2, clearly x equals 2 is a 0. And a lot of times you'll want to factor out the most you can because you might have 3 factors. And if one of the factors is negative, the other factor is positive, and the other one's negative, a negative times a positive times a negative is a positive. And that's what we're going to see in this example here. So in a quadratic, our derivative is linear, and it's really easy to solve a linear equation. This example, we're going to look at a 4th degree polynomial. So we have 3x to the 4th plus 4x cubed minus 12x squared plus 2. And I want to get some information. One's an increasing and one's a decreasing. This might eventually we're going to talk about rectilinear motion, and it will be a particle, and I want to know when's the particle increasing in speed, when's it decreasing in speed. When's it speeding up and when's it slowing down? And that's all related to the first and second derivative. So eventually that's kind of where we're going in the application problems. When's the acceleration, when's the velocity 0 type thing. So here, differentiating this, what do we get? All right? And we'll always set this equal to 0 because those are our critical points. And then look at the intervals in between those critical points. So if I set this equal to 0, I'm going to have to factor. So what can I factor out of this 3rd degree polynomial? 12x, very good. So if I factor out a 12x, I'm left with x squared plus x minus 2, right, equals 0. So can I factor x squared plus x minus 2? Right? Oh, this would be plus minus. Thank you. Plus minus. That look better? So what are my zeros? Very good. I have 3 of them, right? So if I come over here and I draw my number line, I always like to label my number line as I'm evaluating these points to the first derivative. So if I put them on here, I have -2, 0, and 1. Some books and some other instructors teach the method where you list out all the factors in a table and you plug in points in your interval and kind of write them out. I don't make you do that because it can be kind of time consuming, where I think you should be able just to plug in points and say a negative times a positive is a positive. So let's look at this, and I'm going to actually do it both ways. So this is my factored derivative, right? If I plug in a point less than -2, this factor is negative, right? So if I plug in a point less than -2, this factor is also negative, right? Let's say -5 plus 2 is still negative. And then a negative number minus a number is negative. So I have negative times negative times negative, which is negative, right? So all this is negative. If I come between here, -2 and 0, if I plug in -1, I have negative, positive, negative. And a negative times a positive times a negative is positive, right? So then this would be positive. So the other method of doing this is to write out every factor like this. And then f prime of x. So f prime of x would be in this table. And then on the top of the table to write out your intervals. So I have -infinity to -2, right? Then I have -2 to 0, 0 to 1, and 1 to infinity. So now, if I'm in this interval, then 12 times x is negative, right? X is any number in this interval. So a negative number in this interval plus 2 is still negative. And then a negative number minus 1 is still negative. Negative times negative times negative is negative, right? And then if I'm in this interval, let's say I'm -1, I'm negative, positive, negative, which would be positive. You see how it's doing the same thing? When we just do it this way, it's all in your head. And here you're actually showing your work. So if I'm here, I'm positive, right? Positive, positive, negative. Right? Because that would be like a half minus 1, which is negative. Which would be negative. And then here, I'm positive, 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 positive. So then this would be negative, this would be positive. So if I wanted to ask where the function f of x is increasing, what interval is my function increasing on? 2 to 0, union 1 to infinity, right? And f of x is decreasing. When's my function decreasing? -infinity to -2, union 0 to 1. You guys see that? The calculus is taking the derivative. Everything else is just algebra. And then evaluating what it means if your slope's negative. And a lot of times you can just imagine, okay, this is at a negative slope, my function has to then be decreasing. This is a positive slope, my function has to then be increasing. Any questions on that? So the next concept we're going to talk about is the second derivative. So we have the first derivative, which is change in position. So that's slope, right? The second derivative is going to be change in slope. How is the slope increasing or is it decreasing? So the slope can be positive the whole time, but can be getting larger and then getting smaller. But the slope is always positive. Or it can be getting from a larger slope to a smaller slope, either increasing or doing that decreasing. And that has to do with concavity. So I'm going to pull this up here. So let's look at concavity. So if I have a function that looks like this, this is concave up in this interval, and in this interval I'm concave down. Didn't do a great job of that. Okay, right? Can you see? Your book gives the idea of water spilling out. So if I was to pour water on this function, the concave up areas would hold the water and the concave down areas would spill the water. Question?
Does it have to like involve a turn back to
No.
negative slope in the original function to be concave down? Like what I'm saying is that like that appears to just be an increasing part of the original function there. It looks like it just stays constant.
Yeah. So if I give an example of x cubed, this is f of x equals x cubed. This is concave down in this interval and it's concave up in this interval, but the function's always increasing, right? It's always getting larger. So if I was to look at the first derivative of this function, I'd have 3x squared. Well, that equals 0 at critical points, right? At x equals 0. But if I plug in a negative number, say I plug in negative 5, I get positive, right? Because a negative squared is positive. And here, if I plug in a positive number, I get positive. So this is telling me that my function is always increasing. It's never decreasing. But if I take the next derivative, the second derivative, I get 6x, right? So my critical point is still at 0, but if I plug in a negative number, I get negative, and I plug in a positive number, I get positive. So this is the second derivative. So this tells me it's concave down. Oops, sorry about that, guys. Concave down from minus infinity to 0, and then concave up from 0 to infinity. Can you see that from the graph? This point here is called an inflection point, and we will get to the definition later on today. But what I want to kind of show you here, concave up is when I have, my slope here is really small, right? At this point, my slope is small, but it's getting larger. The change in slope is positive. It's getting larger, right? And then at this point, I maximize my slope. And then at that time, I start turning around. I'm not getting larger anymore. I'm getting smaller. So I'm concave down. When your slope is increasing, the change in slope is increasing, you're concave up. When your change in slope is decreasing, you're concave down. So really this comes from 4.1.4. And this tells you when the second derivative is positive, the function is concave up. When the second derivative is negative, the function is concave down. And then when it equals 0, it's called an inflection point. Okay. So I kind of drew this same graph again. This is my inflection point. This interval, I'm increasing slope. And in this interval, my slope is decreasing. Right? Concave up, concave down. Second derivative, positive. Second derivative here is negative. Right? If we go back to the example of that quadratic, just real quick, if I take the second derivative, what do I get? 2. 2 is always positive, right? So that means this function is always concave up. which clearly it's always concave up, right? If I look at this example, which I didn't graph it, I would have to take the derivative one more time and look at inflection points. Turns out the algebra here is not nice. You have to use quadratic formula, and you get like plus or minus. You get -2 plus or minus the square root of 28 over 6, which is a number, but it's not a pretty number. So let's look at an example where the numbers come out relatively nicely. Okay, so we have the function f of x equals x cubed minus 3x squared plus 1, and I'm asking you for the intervals on which f of x is increasing, decreasing, concave up, and concave down. So to look at the increasing and decreasing, you have to look at the first derivative, find critical points, and then test on the interval. And for concave up and concave down, you have to look at the second derivative. So what is the first derivative of this function? Right? Relatively simple. If I factor out a 3x, I'm left with x minus 2 equals 0. So my zeros here are x equals 0 and x equals 2. So if I throw that into the number line, the number line just breaks up your intervals. So everything that happens in between 0 and 2, whatever number you pick, is going to be the same for any number in that interval, because we're dealing with continuous functions. So if I plug in a -5, I have a negative number times a negative number, right? Which is positive. If I plug in any negative number, I have 3 times a negative number, and then a negative number minus 2 is another negative number. If I plug in 1, I have a positive number times a negative number, which is negative. If I plug in, on the other side, a positive number, positive times positive is positive. So now I can answer, when's my function increasing? Negative infinity to 0, union 2 to infinity, right? Where is it decreasing at? 0 to 2. Concavity, I have to look at my second derivative. So what's the second derivative of this function? 6x minus 6, which I can factor out as 6 to get x minus 1. So my 0 would be at x equals 1. So I always like to remind myself what function I'm plugging it back into. So I always label my number line as I'm looking at the first derivative here. Here I'm looking at the second derivative. So if I plug in a negative number, I have a negative number times 6, which would be negative. And if I plug in a positive number on the other side of 1, let's say I plug in 5, I end up with a positive number. Question?
Do you mean that's x equals 1, right?
Oh yes, thank you. X equals 1. Is that your...
Yeah.
Okay, thank you. So now when am I concave up? From 1 to infinity. And I'm concave down from minus infinity to 1. This is also known as the inflection point. Eventually, we're going to learn the first derivative test and the second derivative test.
Second derivative is the inflection point, or?
No, x equals 1 is an inflection point.
Okay.
Does it mean we
And if they want a point, it would be at 1 minus 3 plus 1 minus 3 would be at 1 comma minus 1, right? If I plug 1 back into my original function, I have 1 minus 3 plus 1. So if they want a point, a lot of times they want an x comma y. But you can always find the x component of that. Once you have the x component, you plug it back into the function to find the y component. This is the inflection point of the graph. It's when I'm changing from concave down to concave up. So in this interval, I'm decreasing. So I'm decreasing concave down to concave up. So you can be increasing. So here I'm going from concave down to concave up, but my function is increasing, right? My function is always going up. This is concave, this is concave up, and this is concave down, right? I could also go from concave down to concave up and still be increasing. So this would be down, this would be up. Eventually, you're going to get to the point where I give you all the information in the graph, and then I ask you to graph it. So if I say on this interval you're increasing in concave down, you know that you're going to draw something like this. Versus if you're increasing in concave up. Right? And I might tell you that by the second derivative of x is less than 0 from a to b. So you know that this means I'm concave down. So I need to draw something that looks like this. Right? You can do the same thing with decreasing functions. If I'm decreasing, let's see if I can do this. If I'm decreasing and I'm concave down, I go like this. If I'm decreasing and I'm concave up, I go something like this. Right? So, more like that. So depending on decreasing, increasing, and your concave up, concave down, here the graph of this function, let's look at the graph of this function. So if I was to graph f of x equals x cubed minus 3x squared plus 1, 0 and 2 are my turnaround points. If I plug 0 into my function, I get 1. So the value of the function as 0 is 1. If I plug in, oh, it's just 0 and 2 are my turnaround points, sorry. If I plug in 2 to my function, what would I get? Whatever 2 cubed. Did I graph this one?
Minus 3.
Minus 3. 2 cubed. If I plug in 2 here,
12.
minus 3. So 1, 2, 3. So I have this point. My first derivative tells me my function is increasing until I hit 0. Then it's decreasing until I hit 2. Then it's increasing. Which would make sense because the end behavior of a cubic, as x goes to infinity, and as x goes to minus infinity goes to minus infinity, right? So the end behavior here would go from minus infinity, but here would go off to infinity. So I have the graph of the function looking like this. From 1 is my inflection point. This is actually, if I plug in 1, I get minus 1. So this would be 1 comma minus 1. So you can see I'm concave down on this interval, and then I'm concave up. This is the inflection point. So I've graphed this cubic without actually doing anything with cubic. I differentiated it, then got a quadratic, differentiated the quadratic and get a linear term, and I got all my key features. Eventually we'll talk about maximum and minimum points. So then we have a maximum point here and a minimum point here. And anytime you go from a slope of positive to negative, you're going to have a maximum point. And when you go from a negative slope to a positive slope, you have a minimum point. Eventually we're going to get to more information. But at this point, increasing, decreasing in concavity. Question.
I understand that you got the x equals 1, but how did you get 1 minus 1?
So this is the function, right? So if x equals 1, what does f of 1 equal? Well, I plugged 1. Yeah. So this gives me 1 minus 3 plus 1. So that's 2 minus 3, which is minus 1. Right? So my point is 1 comma minus 1. The x value is 1, the y value is minus 1. Here this point would be 2 comma minus 3. When I plug 2 into my function, I get 2 cubed minus 3 times 2 squared plus 1. So this would be 8 minus 12 plus 1. So minus 3. So that gives me my y point. Question?
So since this is a positive variable,
Mm-hmm.
when you take the second derivative, that's when you get the actual point. But if it was like a fourth power, you wouldn't get a specific point.
You would. You could get more than one.
That's what it is.
In college algebra, there's a theorem that says any polynomial to the nth degree will have at most n minus 1 turnaround points.
Yeah, I remember that.
Yeah. So this is a original polynomial's third degree, but at most it can have 2 turnaround points, 2 critical points, which makes sense, right? If I have a third degree polynomial and I differentiate it, I get a second degree polynomial. And a second degree polynomial has at most 2 roots. And if it has the most 2 roots, that means it has the most 2 turnaround points. So a lot of those theorems in college algebra, their proof was done by calculus-based approach. So you didn't learn the proof at that point because it was over your head. But now you could go and comprehend it more to say, oh, okay, well, I understand if I differentiate an nth degree polynomial, the highest term is going to be n minus 1. So I can have at most n minus 1 factors. So if I start with a 5th degree polynomial, and I differentiate it, I have a 4th degree polynomial, and if I differentiate that, I have a 3rd degree polynomial. So the second derivative has at most 3 inflection points. And you can have multiple inflection points, that's fine.
Because the inflection point is just the change in concavity, essentially,
It's
right?
yes, it's the change in concavity because I'm going from I'm increasing my slope to I'm decreasing my slope, but my slope is always positive.
Sure.
Question.
So the 1, negative 1, how is that an inflection point? Because I just feel like it's still
So
slow.
it's the same slope, exactly. The slope is still negative here, but here I'm going from basically the slope here is 0 to a negative number. So my slope is decreasing, right? And it's the change in slope. And then at this point, my slope is going from a negative number to 0. So the slope is changing here. Here the slope is positive, 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 positive. Or sorry, it's positive, 0, negative, 0, positive. The slope's the same, but the change in slope,
Change in slope is increasing rapidly.
yes,
Decreasing.
it's increasing here and then it's decreasing here. Right? So this is concave down, and this is concave up. And the change is right here. The change in concavity is at this point, the inflection point. All right, I will assign 4.1 when I get back to my office on Wiley. 4.1 will not be due this Monday because we have spring break, so it's due in a week from spring break. So you have kind of a lot of time to work on that. All right, I'll see you guys tomorrow.